Dope. Dope. Oh wait, I heard myself super loud. Oh wait, I heard myself super loud. It must be this. It must be this. Mm. Oh, now I see it was on my own channel on my Windows computer. Great. Anyway. I have pretty much everything I wanted to have for this tutorial. I guess you should push the code, the changes that I made. I did make a few. I'll just say that. And push those. Then I wanted to add an example on using using a full screen quad right before basically my internet went out, which was really frustrating. There are already examples here. Like this inline one. Although even this one's broken with some of the changes that were added later on. Oh wait, it's not broken. Oh, actually I think I know why. Because I made a local edit to my code that pretty much made this match up. But I think by default this window is too large. And it makes it look like that, basically. Oh well, works for me, .jpeg. I wonder if it's worth going over all of this. It's only a fragment shader after all. Although this st variable, this is a pretty mysterious name. Vec2 of half minus st, so this is a vector to the center of the screen. It's getting the angle of that with this arctangent y over x. Increasing the angle with time? That doesn't make a ton of sense to me. Increase. Well, I guess that means this point, the point that's colored this way, is supposed to rotate around the center. And then we have this radius. It's gonna map the angle to a hue with this. Taking the angle divided by 2 pi plus 1/2. So angle divided by 2 pi. Oh no, this is the vec3. This is like an RGB that it's having. Or is it the vec3 part? Oh yeah, it is. What does HSB to RGB take? Oh, this is HSV is this for the H. The radius is saturation and the value is always 1. And so that's how it's getting that colored output. I mean, that's fair, not too complicated. More than I'd want to do for a first example though. I guess the only thing it needed was this resolution. I wonder if there should be something easy I can find from the book of shaders. Also, I should close some of these tabs. Okay, there should be something pretty simple from the book of shaders. Should be. I think this line, for example, is pretty simple. Smooth step 0.2 to 0. And the distance it's using is c.x or sc.y minus x. So it's basically looking for areas where this is nearly 0. So ST, this is going to convert GL frag chord into arrangement 0 to 1. Then y equals st.x. That's sort of confusing. Then it's going to get this color, which is the y part. Get a percent using this plot. And the color it's going to add for the pixel, for the fragment, is going to be 1 minus percent times this color, and plus percent times green. So it's interpolating it percent way towards green. GeoFrag colors is back 4 with that. I wonder why this is taking st.x instead of st.y. What if I change this to y? It's the same. Interesting. Let's see how this does this for a different function. st.x comma 5 for this one. Oh, y here means the function it's graphing, or it's plotting. And it's getting a color based on that plot. Percent minus 2. About 2%. So it's st, which is the current position, y, which is the function. it's going to say, okay, and it's fading on both sides. It's taking percent -2 to go to 0 and percent to be at 1 for the y coordinate. Then subtracting a smooth step. So it's doing the smooth step in both directions. One is beneath the line. Wait, percent -2. Nah, I don't. I could probably figure this out if I looked long enough. But this soon before going over it, I probably just direct people to this rather than try to go over it. Or at least try to go over it by line by line. This one's probably straightforward enough, though. The vector of half minus st, this is fairly straightforward. All the way, yeah, so angle to the center. Let's compute that angle, update it with time. I don't know why the radius would be doubling this. I feel like this should be not doubled. But anyway, following that is fairly simple. Mapping the hue saturation value to the angle, the radius, and then 1. It's not too complicated. So that I can go over. I'd like to go over something a lot more complicated, like my wallpaper background. If I can find a way to run that in Manim. Since it's also just a shader toy, it's basically just this. So if I can get it the right uniforms, then maybe I can run this in Manim. I think it would go right after this. Let's see. Just paste that code there for now. It's gonna look pretty much like this. Give you a pretty similar shader to this one, or scene to this one. And that's a ton of code, though. Okay, so this should run directly. Did I capitalize this? I did capitalize the S. Okay. So great. And then I want to replace this code with all of this code. If I'm lucky, that'll run right away. But it probably won't. At least modulo some variable changes. So I just dump all of this in here. Why is this pi here? Was that part of this? Oh, it is. And why can't I indent it? That was weird. I'm going to assume that I can actually import this full screen quad. And then I'll put the version string in. At least I would if I had any code that had the version string in it still. Yeah. Or maybe it should be like here. So I don't see why any of this math should fail. There might be some uniforms that I'm not passing into this. Oh, this will have to be called main. It should be frag underscore color. This might have to be GL underscore frag chord as well. Oh, it just takes nothing. And it's frag underscore color. So I guess I'll just put that here, I guess. That frag underscore color, then when it writes to the variable at the end, I'll frag color here too. This must use the resolution or something somewhere. I resolution. Is there I time too? Yeah, it does. But those are the only ones, so it should be a fairly simple substitution. Let's see if I can find I time. Okay. And maybe now this still runs. But probably not. Okay. Time used uninitialized. Oh, that's important. Let's see where I used a time. Float time here. I wonder where it would be used normally. There must be a time equals somewhere. U time divided by 2. I mean, it's getting set. Don't know why I have this global like this, though. That is pretty weird. Oh, I have to declare both of those uniforms. So basically like this. Put both those there. See if this is any better. There we go. It doesn't really... I think it used to, if you made it bigger like this, it would actually just get bigger. Maybe that didn't happen. Maybe it just means that the size that you're planning to make it up front. In which case, I can just double these. Okay, and now it looks too small. But if I expand that, it looks a little bit more normal. Okay, cool. Anyway, that's a lot. That'd be good for showcasing what's possible to do with those quads. I call it background quad. And I'll also push that right before. Just probably go right. I should probably move the hierarchical model matrices right after the view visualization. So right about here. I think that makes more sense logically. How much time? A bit more than half an hour to go. I guess I should just make sure all these run. gRPC again shouldn't necessarily be here, but it is useful for testing. So that runs, doesn't do much. Check out this pipeline code. That's correct. That's correct. That's correct. Pretty sure this will all work if the first parts of it worked. Oh, no, something didn't work. So that's cool. Oh, I think it's because I clicked it twice. Is that why? Well, good thing I tried beforehand. Okay, so that was because I clicked it more than once. Okay, so that can showcase all of those. Perfect. And then the half screen triangle. Here. Great. Projection. Cool. Input types. This is basically just to have something that has attributes and uniforms. But that works. Model visualization. Great. Anyway. This works too. Update mesh, I'm sure works. I'm pretty sure all of them work at this point. You just make sure. You can switch this with, for example, put a T here. That'll start moving to the side. Negative T here. They're moving down. Okay, cool, cool. View intuition. Well, it's not letting me stop for some reason. Thanks, Python. Can I close this? Oh, there we go. Okay, and then I'll do the one for the intuition on the view matrix. Okay, so that's going to be working too. Okay, even the translation works. At least the way I would expect. That should be 11. Oh wait, hold on. Yeah, at 1. Then it stops working. Cool. This... Wait, does that work? Start increasing. Yeah, that's doing what it's supposed to do. Y, for example, that's working. X is also working. Okay, so this works. Let's try this, see how that works. It's doing fine. Cool. Then the hierarchy. Yes, that also works. Base-centric interpolation, I think I just went over this. I'll just go through this really quick again. Great. Then we have the background quad. This is the one I just did. Oh, wait. I changed the name. Yeah, I'll probably want to not... Yeah, by default, it won't double this. For the resolution. So the first time it makes sense. Okay. We have the gallery. Which is basically just this. Show off the different colors or the different geometries. Oh, this is basically also the way to go over lighting, I suppose. Oh, and the normal matrix. Yeah. Okay. Then the logo. Cool. So that's everything, all the visualizations. I think for hierarchical model matrices, I wanted to see if I could pose this as a question. Update Earth. No, OMG, it's Lost-ching. Thanks for following. And that actually reminds me, I should find a way to silence those beforehand, just so that it doesn't interrupt me. And I don't know how to do that, so... hope it's not too hard. I guess I could just remove the alert box or something like that. I don't think I have to do this on this site. I don't think. Maybe. Especially since I can't even find the settings. Oh, here, follows. So maybe that's all. Now I test a follow. Nope, still happened. It literally says disabled here. I blame the internet. Maybe I can just remove the box. Which is too bad because I like it being there. Whoops. I should probably learn how to use Twitch. Okay, I guess I just gotta take it out. Then afterward, I'll have to... I should update this to actually, to have custom ones. I'll copy these and then put it on a screen that I don't really use. Like this. Nope, doesn't let me do that. Maybe this? Oh, there we go. I think that worked. It probably didn't. It probably destroyed some random thing. This is why I start this beforehand. I think it did. And if it didn't, then, well, then I get to figure out how to put those back later on. So I guess it means thanks even more for following, because it gave me a chance to debug that. Oh yeah, but what I was doing here is I wanted to... well, this is this that much code? Let me see. You basically only have to see update sun and update moon. So I didn't add the updater for the earth. Okay. So maybe I could start from there. I should be able to ask. Actually, let me just... If I move all of the add commands together, this will do the exact same thing. Okay. Then I can ask, I can say, all right, the sun was added to the earth, and the earth was added to the moon, to its coordinate space, and when I update the sun and rotate it, the earth and the moon rotate around it. So if I want the moon to rotate around the earth, what should I do? And then I could ask, maybe you'd want to do something like this. Which is just rotate the earth with its model matrix. Let's show that that doesn't work. And then you might wonder, why would that not work? And I can say that it's relative to the parent's coordinate space and say, all right, so what we really want to do is this. So I think that would showcase that pretty clearly. Yeah, that code's not too complicated. We still have 20 more minutes. I guess I can push this again. I assume my volume's all right, otherwise, I don't know, maybe at least someone would tell me. I hope someone would tell me. Should test out that the tablet's working. both here, and if I just full screen this. What pictures do I have here? Not are that complicated. I think the most complicated thing that I draw would be for the transformation, or for the translation matrices. Which is basically a picture like this. Yeah, I just want to make sure that I have this right. So I'll draw this, translation, this is 3 long, like this, off a vector, which is 3 long, like this. It's a 1 here, and I'll ask, what happens when you multiply these? And the way to think of multiplying these is by having this 4x3 matrix multiplied by this 3x1 matrix. And then since it's the identity, you'll get this vector back in the first 3 entries. And then for that last entry, you would just get back to 0. Wait, am I thinking of that right? 4x3. Oh yeah, and the last entry wouldn't be even considered yet, since the last row is all zeros, so you'd get this. That's for the first part. Then you multiply the second, or the last entry, which is 4x1 matrix, like this, a 1x1. And then you get 1 times this row, and so you get this back. And so that pretty much explains how translation matrices work. Okay, anyway, that's the most complicated diagram. Everything else I draw will be pretty easy. And I can leave that there if I need it. So I have around 15 minutes before I have to start. Maybe I should tweet about it. You might end up doing that. Or maybe I should see if this site works so I can showcase something related to that. I think if I just don't add those lines to it. I forgot what this even does. Actually, I don't know if the version that's pushed does anything. This kind of does something. I'm spoiling what it does, or what the website does. Even though that was never really something that was secret. Anyway. That does something, which is good enough. Alright, I'm pretty much ready. I just have to wait these 15 minutes. Hey, Jonathan's1212, what's up? I hope you're ready to learn some OpenGL. I did all the preparation I wanted to do now. Maybe I should just tweet it or something. The Manim beginner. Okay. This might be a little complicated if you're a beginner to using it. But hey, you could also learn the OpenGL stuff before learning the non-OpenGL stuff. Try to keep up, and I'll try to make it relatively easy to follow. I don't think there's anything majorly complicated here. Conceptually, at least. Anyway, I'll do a tweet. Why not? I'll just retweet this. I think. I don't really know how to use Twitter. Oh, it's already retweeted. Can you retweet multiple times? I should probably learn how to use Twitter one of these days. I can copy the link to it. I don't think it needs this s equals 20. I'm gonna out myself as a Twitter noob. Like, if this link doesn't update with an embed or whatever, everyone's gonna be like, why didn't you just retweet it? Oh no. When did we retweet this already? Wait. Yeah, I don't actually know how to use Twitter. I guess I'll just link it. And tweet it that way? Or if I reply to it, will that appear? Will people like be notified of that? Gosh darn it. Okay, I'm gonna link it. Don't tell anyone. Wait, I'm gonna search. Oh, the retweet. You can only retweet a tweet once. But you can undo a retweet and retweet it again? Oh, man. I do not have any conclusive evidence that this is beneficial. Okay, maybe when you pin it, that also retweets it or something like that. But I don't know when we retweeted this. Like, if I scroll down, I don't see the retweet. Okay, I'm gonna link it. Don't tell anyone. I'll do it without the s equals 20. Tutorial starts in, I guess I could say like 5 minutes and then schedule it. Or I could just wait until it starts and say that it's started now. Since if it's starting right now, if it's already running at the time that people see the tweet, then it'd be a lot more accessible since people won't have to like click it and then wait. Right? I probably should have figured this out before. I'll just say starting now. Tutorial on OpenGL with Manim starting now. I'll say the tutorial. And then I might as well link my stream instead of linking the tweet that links the stream. Great. And I'll schedule this for today. And I'll do 1 p.m. I'll do like 1:03 or something. So then I would have just started. Yeah. Cool. And I should probably say it on the Discord too. But I can't schedule that. It is a lot easier to reply. I'll just say the same thing. Now, exclamation point. And I'll wait, I guess, the 6 more minutes before I do that. So I can do it right before I start. It would have been nice if I could turn off these LSP alerts. But I have no idea how to do it, actually. Also would have been pretty nice if we just figured out these imports ourselves. But alas, we didn't do that. I wish I knew how to do polls on Twitch. I could ask, like, what your experience level with Manim is. Let's see. No, that's not what I was trying to go to. Is it like this? Is there a way to do a poll from here? I guess not. Ah, you have to be an affiliate. How annoying. Yeah, okay. Well, I guess I can't do that. So, anyone know any good jokes? As I am basically just stalling for time at this point. And I'm stalling in a good way. Since I know everything's working now. I should probably go to the start of this. I wish the person who wrote this would finish the book. There's a lot of useful information here. I guess it's good that I know everything works here. That's a neat visualization. Who is Joe? I don't know who Joe is. Where did Joe come up? Which clock should I use? Oh, hey, it says 1 p.m. now. Okay, so I'm gonna go on and save this and then get started. And mute this. Don't need that running. For like all of posterity. So I'll go on to and go to my face and say, all right, so thanks for showing up. And this is going to be a tutorial on using OpenGL with Manim. And if you want to see the code that I'm using here, that should all be hosted on GitHub. There might be a few small edits that I did right before getting started on this. And I think if you use exclamation code, it'll just link you to the code I wrote. So if you want to either, it might be complicated to set up now, but if you want to see what I'm doing or go through that later, if that's where it is. I'll also link it on all the places where this is stored and stuff. But in a general sense, this is going to be a lesson on how you can use OpenGL with Manim to render things in 3D and render a lot more quickly. Yeah, and it'll probably use some, it'll be a lot easier to have some experience with Manim, but if you don't, then it's not a lost cause. You could still, should be able to follow this stuff relatively easily. So with that, I'll just get started on at least the very beginning stuff of what you'll have to know. So to use OpenGL at all, the first thing to understand is this concept of a shader. And there are two types of shaders that we're going to be looking at for the most part in this tutorial. And those are vertex shaders and fragment shaders. Now, vertex shaders are going to define the geometry, so sort of the shape of an object, and fragment shaders are going to determine the color and the way that it appears when you look at it. And so with that, I'll just jump right into the way that we can interact with these shaders, which are used to draw things on the screen, and show you how we can do it with Manim. So I'll get started on a conceptual level first. With the scene. Okay. So as I said before, you're going to start with a vertex shader. Actually, I think I can just full screen this. You're going to start with a vertex shader, and a vertex shader is going to take an input as vertices. And vertices, and the way that you interact with them in the code, are going to be a list of data points. And each of these data points will have the same fields, which are called attributes. So for example, this is a list of 3 vertices, and each one has 2 fields, a position and a normal. And so you'd list these out in the code, and then you'd pass these to a vertex shader. The job of the vertex shader is to take these vertices, these data points, and transform them into vertices in the way that we understand them. So 3D coordinates, essentially. So that's the job of the vertex shader. And you can use any computation you want to take that data and output these points. So after the vertex shader, we're going to go through a step called primitives generation. And what this consists of is taking those points in 3D space and using those to generate primitives. And a primitive is essentially one of the things that OpenGL is capable of drawing. So the most common one is triangles, and that's the one I'll be using pretty much this entire tutorial. But there are also ones for lines, and there are ones for points. But this is the point where those are going to be generated from that data. After that goes on, it's going to go through a rasterization step. And rasterization, as this image sort of implies, is taking those primitives and breaking them into pixel-sized pieces, which are called fragments. And so it's sort of like pixelating that shape for the resolution of your screen. So to do that, these will be fragments, and those fragments are going to be passed to a fragment shader. And as I said before, the job of the fragment shader is going to be to determine the color for each of those fragments. Okay, so that's going to color it. So after this, there's going to be a blending step. And the purpose of blending is to determine, okay, so say there's a shape, or there are 2 shapes that are right in front of each other, and they have different opacities. Well, then for each of those pixels, which is covered by 2 shapes, we're going to have to find a way to determine the final color for each of those pixels. And so that's determined by blending. So we're going to blend multiple fragments together, potentially, to get the color for each pixel. Once that's done, we're going to write that data from the fragment shader into what's called a frame buffer, which is essentially a space of memory used for drawing things. That's essentially all it is. That frame buffer will be passed to the OpenGL API, and you'll get something written to your screen, drawn to your screen. Okay, and so this will show an overview of all those steps coming together. So I'll just go through this one more time really fast. You'll have vertices, which is just lists of data points. The job of the vertex shader is to take that data and output positions, 3D coordinates. From those, OpenGL will generate some primitives, which is usually triangles. Those triangles will be rasterized into fragments. Those fragments will be colored in the fragment shader, blended together, and written to a frame buffer. Then you'll see it on your screen. There's a question: how does the GPU find the region based on the given points? You don't have to worry about that. More or less just magic. um, you, yeah, it'll just know it. You'll have to specify your viewport when you're using OpenGL, so you will have to pass it how wide and how tall your screen is. And once it knows that, it'll be able to determine it on its own. But we'll end up going into more detail about how that's done in just a second. Another just fun fact is this is 3D scene. So that's cool. Is fragment and pixel a bit synonymous here? No, fragment and pixel are not synonymous. Oh, I didn't mean to close that. Darn. But the difference is a fragment is a pixel-sized piece of a primitive, and a pixel is a location on your screen. And so there could be multiple primitives that contribute to the color of an individual pixel if those have different opacities. So you have, like one shape with opacity half, and that's in front of another shape that has opacity half. Those are then the fragments that are overlapping will be used to determine the color of an individual pixel. So that's the difference. Okay. So that's essentially the pipeline. Now let's get into doing this, or actually using Manim to do this. This is a shader. It's actually two shaders, but it's a shader object, which is something that exists in Manim 0.9. And the way that you'll instantiate one of these is you'll pass it a context, which is essentially a handle to the OpenGL API for your computer. And then you'll have to give it a vertex shader and a fragment shader. So since there's two of these, maybe it would make some more sense to call this OpenGL pipeline or something like that, but this is what we'll use for now. And this vertex shader doesn't do anything special. It just takes in a position. So this shader requires vertices with a single attribute, that's the position. And the way that it specifies a coordinate to output based on that position is by writing to this variable GL position. So this just takes it and outputs it, nothing fancy. You'll notice that it's taking in a vector 3 and it's outputting a vector 4, which might seem a little weird. We'll get into why that happens in a bit, but for now, just take it for granted that you put an extra 1 here. And then there's a fragment shader. And the fragment shader, the job of the fragment shader is to color each fragment. And in this case, it does it by writing to this variable frag underscore color. And this is RGBA. So this is just writing red. So it's just the color red. So yeah, that's our shader. Doesn't do much. Just outputs the positions you give it and colors the primitives red. So then we have to supply that vertex data, and here's how we'll do that. We'll create this NumPy array, and you basically have to construct this NumPy array so that it has data types for each of the attributes that you're passing in. So in this case, there's only one attribute, and so the data type has only position. That's the only one. So this shader doesn't need normals. Now there's a question. And no, this one doesn't need normals. That was just an example to show that you can have as many attributes as you want. But in this case, for this example, we're only taking one. All right, so these are our positions, -1, -1, -1, 1, and 1, 1. Then we combine these together in a mesh, which is another Manim object. And then we just add this mesh to the screen. So nothing super fancy. Won't deal with this stuff yet. I just won't even deal with that yet. We'll get to that in a bit. And before I run this, I want you to take a while, take a little time to think of what you'd expect this to do. So from what we know already, we know there's only 3 points, so it's going to be one triangle, basically. And we see there's -1, 1, or -1, -1, -1, 1, and 1, 1 are the 3 points. So we'll probably expect something like -1, -1, -1, 1, and 1, 1. So that's a triangle. So we'd probably expect to see something like that, and we'd probably expect to see it shaded red. Right? And there's probably more details that'll be there that we don't see right now, but that's generally what we'd expect. So I'll render that. And that's kind of what we see. We see a triangle here. It's kind of oddly shaped. It isn't half of a square. Instead, it's half of the screen. And this is because OpenGL understands drawing things in what's called normalized device coordinates. And normalized device coordinates are these coordinates where it'll only plot things in the range from -1 to 1. And it'll do that in the x and y and z directions. And -1 is, either the left side of the screen or the bottom of the screen. 1 is the right side of the screen or the top. And +1, -1 is just arbitrary. You can't see the z coordinate on a 2D screen, but if things are outside of that range at the z direction, they won't be drawn. So this is more or less what we'd expect. It's just taking into account this idea of normalized device coordinates. Okay, and to see that sum, I can add in this code, and this code just allows interacting with those points. Okay, so I have the same scene again. And now this GUI is updated to let me move these points around. So here's P0, and you'll see its x value is at -1. If I move this to the side, you can see how the triangle changes as the x coordinate of this point is moved. Same with the y coordinate. And we'll get to the z coordinate in a bit. And you can see this for each of these points. Something interesting to note is that these points will only appear if they're in the range from -1 to +1. And if they go beyond 1, they're no longer on the screen anymore. The triangle doesn't disappear or anything, but the parts of the triangles that are outside of that range are clipped off. Now if we get to the z coordinate, so I'll change the z coordinate of P0. When we edit that, we don't really see anything until it passes -1. When it passes -1 or +1, the triangle starts disappearing starting from that point. And what we're seeing is this part of the triangle is moving outside of the range from -1 to +1 in the z direction. And because of that, that part of the triangle is being clipped off. And so that's what you're seeing here. That part is moving outside of that coordinate space, and so it's disappearing. And so that's how this is working conceptually. And that'll happen for any of these vertices that moves outside of that range. Note that there's no perspective. If we stay in the range from -1 to +1, then change the z coordinate doesn't do anything. Because in these coordinates, OpenGL expects that perspective to be handled before it gets to this point. All right. So that is that. So then there's a question right off the bat. It's like, okay, obviously nobody is going to use this coordinate space. There's a really, you can't even draw cubes correctly, because if you draw a cube in whatever coordinate space you're using, and you pass that to OpenGL, it's gonna, stretch it by the aspect ratio of your screen. So the immediate question is, how do I convert my coordinate space, the one I want, into coordinates that OpenGL will understand, which is normalized device coordinates? And the answer to that question is what's called a projection matrix. So this is the next scene. We have, I can never tell if this is big enough. There we go. This is the next scene. We have, this is the same shader actually, just some more spacing. We have the same shader. We even have the same data, the same triangle. Now the difference in this case is that I'm going to declare this projection variable, which is a matrix. And I'm just going to convert or scale each of these dimensions. So the width, which is taken from Manim, this is the frame width from Manim, I'm going to divide out that width and multiply by 2. And why 2? Well, in normalized device coordinates, the width is -1 to 1, so it's 2 wide. The height is from -1 to 1, so that's 2 high. And it's also 2 deep. So I'm just going to take out the width, height, and depth that I want to use in my space and multiply by 2, which is what OpenGL will expect. Okay, so just following through this code some more. This is sort of just a technical thing. These are row vectors, and matrices are for column vectors. So the way that I transform this is that I take this attributes, I transpose it, so then it's a column vector. Then I multiply it. Then I transpose that again, so it's a row vector again. Okay, and I think I'll just run this now. Well, yeah, I'll just run this now. Is a projection matrix based on screen size? I mean, should I explicitly mention the dimension of the screen, or will OpenGL? So there's two parts to this question. The projection matrix isn't based on screen size, it's based on the coordinate system that you have for your scene. So you can choose your own coordinate system depending on the project you're doing. And regardless of what you choose, you'll have to transform that one into Manim's coordinates. Now, separately from that, the user might be viewing your thing on like a different sized screen. And so you'd have to take that into account when you're either determining your space or thinking of how you want this to appear. So you will have to take that into account, but it's not something that OpenGL is aware of, other than using that in normalized device coordinates. If that makes sense. Yeah, no problem. Okay, so when I move the slider, this is going to show the progression from having the regular triangle that I had before and the triangle transformed by that projection matrix. And the beauty about this, if I show the grid lines, is that when the triangle is transformed by the projection matrix, it's aligned exactly with grid lines from Manim's coordinate space. So it comes from here, and it comes exactly to grid lines in Manim's coordinate space. Oh, you can't even see the GUI. I'm just sliding this. And so that's great. Now we see something much more close to the picture that we were expecting, the half of a square. There's sort of a faster way to resize this. And that's from just multiplying by this projection matrix. Yeah, so that's great. Now we have a way to anything that we want to see in OpenGL. We can transform it. We can, well, specify it in our own coordinate system, transform it with the projection matrix, and then when we pass that to OpenGL, it'll appear in our coordinate space. So that's pretty nice. At this point, I'm going to take some time to talk about the different types of variables you can pass to shaders. So, we've already seen attributes. Those are data points that you just specifying your vertices. Oh, I should have looked at the code first. We can look at it now. So this is the shader that I'm using for this. Not so complicated. It just has, well, in this case, it's taking in that projection matrix. Rather than me doing that, I'm passing that that matrix into the shader. And that's done with what's called a uniform. And uniforms are variables that are accessible to both the vertex shader and the fragment shader. It's especially useful for projection matrices, because if I'm going to multiply every vertex by the projection matrix, it doesn't really make sense to pass that for each vertex. I can just pass it as a uniform and then multiply that by each vertex like this. So that's a uniform. Then there's what's called a varying, which is a variable that's passed to the vertex shader, or passed from the vertex shader into the fragment shader. So this variable, color, is computed in the vertex shader. It's saying that if the x position of one of these vertices is positive, that's going to set that color to blue. Since this is RGB, this is blue. And otherwise, it's going to be red. And then the fragment shader is going to take in that varying variable and set the color based on that. Other than that, I think this is just a regular, is the same thing. The same triangle, create a mesh in the same way, create the projection matrix in the same way. Something to note when passing matrices to OpenGL is that OpenGL reads matrices in column major order, meaning you can't pass in a row at a time. You have to pass in a column at a time. I think it's some performance optimization thing. And so that's why I have to do this. I have to transpose it so that all the columns become rows, and then I do ravel, which essentially stretches out so that this 2D array will become one dimension, where it'll go row-wise. So that's why I pass it in this way. And other than that, it's the same thing. It's aligned perfectly with Manim's coordinates, like you can see here. And it was something that I should have mentioned. I can change this up as I want, and this will update in the shader. So if I want this to be purple, if the x coordinate is positive, I can update that to a 1. And now it's going to be purple. It sort of looks like this magenta, but that's combining red and blue to get some sort of purple. And then if I wanted this to be green for the other two coordinates, I can do this. And then it's going to interpolate from purple to green. All right, or you could do something else like this. You could just, so what if I wanted this to happen? If the y coordinate is positive, just change that to a y. Then it'll do it that way. And you could do this like any way that you want with these conditions. Great. And so the purpose of this is just to show that this shader is using all three variable types: attributes and uniforms and varyings. Where do you tell it to do a gradient? That's a good question. And that's done automatically, actually. Actually, I can just go over that now. For any of the data types that are passed into the vertex shader, the vertex shader is going to run once, essentially, for each vertex. But the fragment shader runs once for each fragment, and there's a lot more fragments than there are vertices. So then there's a question of, if you pass a variable to the fragment shader from the vertex shader, how do you get the value of that vertex, of that variable in the fragment shader? And the answer is by interpolating them. And OpenGL uses what's called barycentric interpolation, which I can just go over now. So this is a triangle. Oh, wait, let me get rid of that tablet. this is a triangle. And for this example, there are 3 different colors for each of the corners, although you can't see the green one. This is green. And this is a fragment, so this is one part of that triangle. And the way that we determine the color for this fragment is that we'd compute these areas. Since this fragment divides this into 3 triangles, which have 3 areas. Then we compute these lambdas. So lambda, oh, well, it's just going to tell you the whole thing. Each of these lambdas is the fraction of the area of the triangle opposite each vertex relative to the entire area of the triangle. So you compute those lambdas, each of these lambda i's. Then the color of the fragment is this weighted sum. Lambda 1 times f1 plus lambda 2 times f2 plus lambda 3 times f3. So that's what OpenGL is doing in the background. So yeah, if this fragment is super close to this red corner, then the area of the triangle opposite that corner is going to dominate the triangle itself. And so lambda 1 in this case is going to be very close to just 1. And so that color is going to be very close to just red. And that's going to be the same thing if it's close to this corner or close to that corner. It's going to vary with the areas of these triangles. So that's how, so I don't tell it to do a gradient. That's just what it'll automatically do. Okay, cool. Okay, so that went over attributes, uniforms, variants. We went over barycentric interpolation early. Thanks. So now let's get back to this idea that we had before of using a matrix to transform a mesh. So we had this idea of taking a mesh that was in the wrong coordinate space, using a matrix to move it into the correct one. So now we have this next question of, all right, if we wanted to move around one of these objects, how would we do that? It's like, well, there's this one idea, the natural idea, is we could just take these positions if we wanted to like move this to the side and just add 1 to them. So fun fact, attributes are not writable. So I'm just going to declare a new vector. And I'll just say writable position at 3. Oh, not at 3. I'll do dot x plus equals 1. Then I'll multiply the writable position. Okay, so if I wanted to move this aside, I could do that, and then it moves to the side. And I can move it to the side some more if I wanted to keep doing that, for example. Yeah. But that is really dumb, because we hard-coded this transformation into the shader. Every object in the world is going to be moved to the side like this. It's like not configurable. We'd like to have a better way to do things like, and it's like, what if we want to rotate this? What if we want to do like anything? Hey, thanks a lot, Mike Bateria. How do we do like any of these transformations? So it's a 4 Manim coordinates. So the 4 is Manim coordinates because we do projection afterwards. Sorta, yeah, that's part of it. But we'll get to the extra vector or the extra entry in a second. But we're looking for this idea of how do we transform this so that to find a way to transform these in a way that isn't silly like this. Okay, just want to bring that back. And the answer is with what's called a model matrix. The idea behind a model matrix is that we associate each object with a transformation matrix, which will encode, you know, any transformation that a matrix can encode. Then we're gonna multiply each position in our objects by that model matrix prior to projecting it. Now, this is super useful because it means I'll just run the visualization of this so you can get an idea of it. Yeah, this is super useful because it means if we want to transform an object, all we need to do is transform its model matrix. So this rotation for the Z component, I can move this, and this object will just rotate on its own. And the reason for that, well, not on its own, but the reason for that is that I'm updating the model matrix. And the model matrix is being used to transform each of the positions in this object. And I can do that around the y-axis for pretty much the same thing. Around the x-axis, I can scale it. And interestingly, I can even translate it. Okay, so I can get into, I can get into what the code's doing. Basically, I added this updater, which is, it looks like it's too long for you to see it. And this updater, and on each frame, it's going to compute a translation, rotation, and scale matrix based on the inputs from this GUI. And then it's going to update the uniform, which is how you set that uniform. It's going to update the model uniform with the resulting matrix. So the model matrix of this object is being continually updated to scale or rotate or whatever. Yeah, and then I'm passing in the projection matrix just like this. Model matrix is initially the identity. So this that I'm passing in for the projection matrix, I'm using what's called an orthographic projection matrix, which is essentially, it's doing the same thing that I was doing in the prior example, whereas basically dividing by my desired world coordinates and multiplying by 2. This is essentially a shorthand for doing that. And this near and far is just determining the depth, how far in front and behind in the Z direction I want this to go. So this is essentially just a shorthand for what I was doing before. And with that, we have model matrices. Something interesting to note, these model matrices, all of them, are just transformation matrices. So if I look in the Manim code, scale matrix. Okay, so this is Manim code, and this is the code for the scale matrix. And it's essentially just taking what's almost the identity and then scaling the X, Y, and Z components. But not this mysterious fourth component. If you want to see the rotation matrices, well, it's combining X, Y, and Z rotation matrices. And these are just, well, this one is basically just the rotation matrix that you learned in high school. But you probably in high school only learned this part of it. And we're making this one part of a larger 4-dimensional matrix. And that rotates it around the Z axis. And then same thing for the X and the Y. But here's something interesting. Normally, the transformation matrices that you use don't allow for translation. Because the transformations that it does are for objects centered on the origin. So there's sort of a question of how are we able to translate it? And this is where this fourth coordinate comes into play. Because since we have that extra coordinate, that fourth one, we can leverage that to put in a translation into this last column, and then that'll be used to translate the shape. Okay? And the way that would work, just briefly, if you want to go into the math, I'll just clear this, is I will have this matrix, which is a 4x4 matrix. And this will require a little bit of linear algebra knowledge. What if we have just the identity matrix here and it's size 3? And then here we have some translation vector, which is also size 3. Here we have a 1 and here we have zeros. So this is the translation matrix. Then we're going to multiply this by a vector that has this extra entry for a 1. So it's going to be some arbitrary vector denoting a point and then just a 1. And what happens when we multiply these? Well, we can split it up, and we'll first get a multiplication of this 4x3 matrix, and we can multiply that by this 3x1, sorry, matrix. And what will we get? Well, we're multiplying this vector by the identity. So that's just going to be the same vector back. And for the last entry, that's all zeros in that row. So that'll end up being a 0 when we only do this part of the multiplication. And then we'll have to do the rest of the multiplication. Oh, this is too long. This is the 4x3. Then we do the rest of the multiplication. So we'll do this 4x1 and multiply by just this. And this is obviously just a 1. And so we're going to get back the translation vector. And then we're going to get back this 1 since it's here. And so the net result is that we've effectively added this translation vector to the initial vector. And this is such a useful concept that in order to be able to do this, we add this extra 1 to every single vector, or every single position. And we add this extra row and this extra column to every single transformation matrix because it's that useful and that easy to be able to translate things this way. So that's the way that the translation works. Cool. And so voila, now we can transform around shapes. I put this little scene together. Do we ever change the projection matrix to object, or is it the same across all objects in a scene? Good question. It's the same across all objects, or all objects. I keep calling objects objects. It's the same for all of them. Changing up the projection matrix would essentially mean changing the way that that objects are projected onto the screen. And it wouldn't really make sense to project one object one way and another object a different way in the same scene. The projection matrix essentially, it encodes your lens of your camera, quote unquote. So having that different for different objects would be a sort of strange thing to do. All right. I put together this scene to sort of just highlight what we can do. This shader, pretty much the same shader. We are passing in a projection matrix and a model matrix. We are transforming with both of them. And we're just coloring this red. And here I'm passing in the projection matrix and the model matrix. This is not a triangle. This is a square, actually. And you can see that as if you just separate this. So this is the same triangle we've been using. And this is the other side of it. So we have -1, -1, 1, -1, and then 1, 1. So that's the bottom right half of that square. So we have a square this time. And what I'm doing this time is on each frame, I'm updating the model matrix for this square with this. So I'll run that. What was this called? Update mesh. Cool, so this isn't doing anything. T3 changes the translation, and I3 controls the rotation of the vector. Matrix is basically a relationship between the new position and the old position. I don't think his question was related to translation matrices. I think it was more related to projection matrices, but that's essentially true. The way you described that. Okay, so this isn't doing anything. If I wanted to just see the way that transformations affect the shape, I could, for instance, put a T here, and this is moving with time this way. I could do this in the X direction and the Y direction. It'll do that. I can see how scaling works out, or this will be stretching. And I'm surprised that didn't crash, actually. Actually, I know why that didn't crash. If I put a 0 here, I think it would crash, but I started at 0.1, not 0. This should scale it in the X and Y directions. Quote unquote shearing is like this. I don't know how it works that well, but if you really wanted to, you could download this code and play around somewhere with this. This essentially just shows you the way that transformation matrices can update your mesh. Is this what is happening under the hood if I call animate.shift in Manim via OpenGL render? Unfortunately, it's not, and I wish it was, but it isn't. The shift function is essentially a legacy. I don't know if legacy is the right word, but it just adds 1 or adds whatever the shift value is to each of the vertices, which is less efficient. If you have an object with like 1,000 vertices, right, you could add a vector to each one of those vertices and that'll work. Or you could update the singular model matrix. You could just update the model matrix of that object and that transformation will happen on the GPU. It'll be super fast and it's basically better, but that's not what happens with animate.shift right now. Okay. Then there's the rotation matrix. If you mess this up, by the way, it does something weird. Isn't that wild? Anyway, this is just sort of showing that off. Pop quiz. How many vertices are in this mesh? This is where I wish I could do a poll, but I can't. So, 6. Yeah, that's basically right. It's really an underspecified question. Okay, 6. Yeah, okay. 6 is basically the right answer, but in Manim, is Manim using model matrices at all? It can, but only if you use them explicitly. It won't happen underneath the API. But you'll notice this vertex and this vertex are, well, they're the same vertex. They're the exact same data in each entry. The same thing with this vertex, this vertex. And so we have these vertices, these exact same vertices that we're passing to the shader twice. Doesn't really matter in this case. But if we had something with like a ton of vertices, it's going to slow us down to have this extra space. And luckily, OpenGL comes with a way that if indices are exactly the same, we don't have to pass them to the shader multiple times. And the way to do that is with an index array or index buffer. The way you do this in Manim is by doing this. And so now I don't have to repeat those two vertices. I can just put in, this is the upper left triangle, and this is the lower right corner. And then it's going to share the rest of the vertices. And then I can just set these indices. And this is going to create an index buffer under the hood. So 0, 1, 2, that's the first triangle. Then we have 0, 3, that's the corner of the bottom right triangle. And then 2. So, I mean, you can see what's going on here. It's indexing into this array. So I can run it this way. You're going to see the exact same thing. But this time, I'm saving those 2 points. All right. So I just wanted to mention that that's something you can do if you're passing in the exact same points. Cool. So now we know how to create these objects. We know how to render them. We know how to move them around with like anything you can do on a matrix. I had this thought of, I guess you can have a model matrix that isn't an affine transformation. This is basically used for affine transformations. I guess you could put in like E to each of these entries. You could do something crazy. But if these matrices aren't invertible, you could run into trouble later on. But I guess you could, in principle, put in something insane, and OpenGL would still render it. But anyway, let's say we wanted to use a camera. We wanted to have a camera in our scene. How would we do that? Or what would it even look like? Hopefully I can stop this. Nope, it's taken on a will of its own. Maybe? There we go. What would that look like? If I was holding a camera, I guess like this, in front of this scene, and I moved that camera in the positive X direction, which is, I don't know, that way for me, to the right. How would that be reflected on the screen? Well, I move the camera to the right, then the screen would appear as if the object is moving to the left, right? And if I move that camera up, it's going to look like the object is moving down, up, down, like this. Yeah, that's okay. Essentially, some of this stuff I understand completely. Some of it seems like I need more math knowledge. That's okay. If you just like mess with this stuff, especially if you look in the code, you'll just get a sense for it. Yeah, but if essentially if I move this camera in one direction, some direction, it's going to look like the object is moving in the opposite direction. And if I were to rotate that camera, say, so the z-axis is coming out of the screen. So if I rotate it around the z-axis in the positive direction, and it's using the right-hand rule, so that's counterclockwise, the object is going to appear to move clockwise, right? If I rotate a camera counterclockwise. So it seems like the pattern here is that any transformation I apply to the camera, I want to apply the opposite transformation to each object in the scene. And in fact, that's exactly what we do to represent a camera. So this is our shader. We have another matrix. You can never have too many. Then we have a model matrix, a view matrix, and a projection matrix. And for each position, we're going to transform it by the model matrix, and then the view matrix, and then we'll project it to the screen. it's like, okay, so what does this view matrix do? Well, the view matrix represents the camera, and since any change to the camera, or for any transformation to the camera, the opposite seems to happen to the objects. The view matrix is the inverse of the camera's model matrix. And there's a few things to mention right off the bat. First thing, the camera looks in the negative z direction. So this is what we're seeing here. Maybe I should just save this. The camera looks in the negative z direction. So we have something like this, and we have x, y, and the camera is up here. It looks in the negative z direction, because this is the negative z direction. And this is a right-handed coordinate system. You should be using a right-handed coordinate system, so z is this way. Okay, so this is why this 11 is here. Oh, whoops. This is why this 11 is here, because I'm putting the camera 11 up this way. It's looking at the negative z direction. So that's what this is. And you'll notice that now for the orthographic projection matrix, I have a near plane, or well, I have this entry near, which is 1. This entry far, which is 21. And the reason for that is so that here's the camera. Here's the camera. It can only see things between this space, or between this plane, 1 in front of it, and this plane, 21 in front of it. So essentially, this means the depth is 20. Okay, so that's what these settings are. Other than that, we have the same, our trusty triangle. And what's happening on each frame is this time I'm taking the camera's model matrix, which is the product of that translation, rotation, and scale. I'm inverting that, and that's what I'm passing into the view matrix. Okay, so the view matrix is exactly the inversion of the camera's model matrix. Okay, and so now let's see what happens. If let me clear that. If I move the camera in the positive x direction, actually, wait. This is the model scene. I was thinking, oh no, not this one. Okay, move the camera in the positive x direction. The object moves in the negative x direction, which is what you'd expect. If I move it in the positive y direction, the object appears to move down. If I move it in the z direction, I think you don't see anything. Yeah, you won't see anything for a while. If you move it really close, then eventually it'll pass past the near plane, and then it'll vanish. So remember, the camera can only see things between 1 unit in front of it and 21 units in front of it. So if I move it closer than 1 in the z coordinate, then that object's too close to it and it disappears. Move it back, I can see that until I get like further than 21 away. Okay, but that's default to 11. If I rotate the camera in the around the x-axis in the positive direction, Well, the x-axis is going to the right. The right-hand rule, that's going to mean the camera is looking up. So I'd expect this object to go down. And that's what I see when I increase it in the positive x direction. And these other things, for example, the y-axis going up. Right-hand rule, if I rotate that in the positive direction, I'm going to be looking to the left. So I expect this object to go to the right. And that's what I see. And so on and so forth. The z, that's me rotating the camera around the z-axis. You can scale a camera. Doesn't super make sense, but you can do it. Also, if you put it to 0, it will crash. So I'm not going to do that. And the reason it'll crash is because you have to invert this matrix. And if you put the scale to 0, it'll become singular, and you can't invert it, and it'll just crash. Scaling a camera doesn't super make sense. Oh, you couldn't see the GUI. But this is how I was scaling it. Scaling a camera doesn't super make sense, but it works out mathematically. You could also do like other weird stuff. You could like exponentiate the view matrix or something crazy like. Actually, I guess not. It has to be invertible. Like you can do any invertible thing you want to the view matrix, and then that'll work out. Is the model matrix always invertible? Unless you put the scale to 0, yeah. The model matrix basically is usually only used for affine transformations, which are invertible. It's very obvious when they're not invertible. Like if you put the scale to 0, I'll just do it. If I put the scale to 0, this will crash. Oh, hey, it didn't crash. Oh, there we go. And get the singular matrix. But if I like translate it really far or I rotate it a lot, that'll never crash. It's pretty obvious when this does and doesn't crash. Let me see if I can... Unless you're doing something like really crazy, that won't happen. How does the camera capture other objects in the scene? I would just add other objects. So... That's actually a good question. For each object that we pass to the scene, we'll have to also pass in the view matrix. So I have this mesh. I should be able to make another mesh like this. Yeah, but why would I do that? I can make another one like this, and I just have to also pass the view matrix to this one as well. So that's what I'd have to do. So I'll just give it new attributes. Let me just increase the x coordinate of all of these. Okay, so now I'm not updating the second one, and I move the camera. Oh wait, they're sharing the same shader. They're sharing the same shader, and so I am automatically updating it. Okay, well I don't want to write a new shader, but that's what you do. I guess it's especially easy if they share the same shader. You don't have to do basically anything at all. I guess that should answer the question. But yeah, these are past the same shader. But if these are rendered with different shaders, I have to pass the view matrix to both of those. Cool. All right, so each object gets a view matrix and the same view matrix for all, yeah. Also the same projection matrix for all, pretty much always. The only thing that changes between objects is generally the model matrix. All right. So I'm going to show a scene that just showcases everything we learned so far. So we have model matrices that can transform objects. We have view matrices that encode cameras. We have projection matrices that determine what we can see essentially in the scene. And we're going to put those together. And it's going to crash. Just kidding. Okay. That's a pretty cool scene. We have our trusty triangle. He's grown up a bit. He's still just rotating around the x-axis. That's all this is doing, is rotating around the x-axis. We can see its model matrix down here. It's just, you could like put this into Wikipedia, check the X model matrix. It's exactly that. We have the view matrix, which is the inverse of the camera's model matrix. So that updates as I move the camera around. And yeah, the model matrix is being updated. The view matrix is being updated with the camera. And that's basically it. So between the previous scene and this scene, there's no new conceptual information. This is sort of just showcasing what we've learned so far. And this is the shader that's being used. So it's passing in this model matrix, view matrix, and projection matrix, taking the vertices of this triangle, appending that extra 1 so that translations are possible. And this works with homogeneous matrices. Guess I should go over homogeneous coordinates. Then it's transforming with the model matrix, view matrix, and the projection matrix. The fragment shader is just outputting the same color, red, for all of it. Cool. And now I can do this. This is showing the same thing from a different view. So yeah, we still see this triangle, still rotating around the x-axis. This just shows, additionally, where the camera is within this 3D scene. And this is what the camera is doing. You'll also notice that this text that you thought was 2D is secretly 3D. Since the model matrix isn't really a thing in Manim right now, I guess the view matrix isn't either. If you use the OpenGL renderer, then it will use a view matrix. Mobjects have also been retrofitted with model matrices too, vectorized mobjects. So if you look at the attributes of a vMobject, it does have a model matrix, and if you update it, it will be reflected. There's just no indication that it's there. Basically, you have to be me, or like look at my commits to know that it's there. But it's there. Okay, so this is really just showcasing everything we learned so far. Cool. You might wonder, okay, how is this text fixed relative to the camera? How do you think I did that? Well, I guess it should be possible with just doing enough math, but that would be really tedious to get exactly right. The real answer is that I added these objects as a child of the camera, and I configured it so that the model matrix of this text, is equal to the product of the hierarchy of objects that it's a child of. And so what does that mean? Well, if I have an object, so I'll just call this O1, something like that. Then I have a child, which is like O2, child O3, and say this has model matrix 1, model matrix 2, model matrix 3. Then this is configured so that the effective model matrix of O3 is M1 times M2. Whoops. Times M2 times M3. Okay, so this is the way that it'll effectively work. What that means is I can do something like M3 is just a translation relative to M2, and then as I move O2, O3 will automatically be moved as well. And we can get some better intuition for that in this next example. Okay, I'm going to comment this. And let's just look at what this code is doing. There's a sun and an earth and a moon. Just take my word for it. They're all spheres. They're not fancy. They're just spheres. And then I'm taking the model matrix of the sun and I'm rotating it on each frame. I'm multiplying it by the Z rotation matrix again. So this is going to make the sun rotate. Now the earth is added not to the scene, but added to the sun. And the moon is added to the earth. Not the scene, but the earth. So let's see what that looks like. Okay, it looks like this. But that doesn't really, it's not doing what we want it to do. The earth is going around the sun, so that's cool. But the moon isn't going around the earth. And you know, why would it? We're only rotating the sun. Now, because the earth is added to the sun, and I also made the earth's model matrix be this translation. I guess I scaled it too, but mostly it's this translation. And the moon's is also a translation. And so they are rotating too. They're rotating because the sun is rotating, but I want the moon to rotate around the earth. And how would I do that? Well, when I updated the sun, it made the earth go around it. So if I wanted that moon to go around the earth, maybe I can update the earth. Now, what you probably think of doing is something like this. Say, okay, well, I'll get the Z rotation matrix, and I'll update the Earth's model matrix with that one. And so that'll rotate the Earth, its coordinate space, and that should update the moon too. And that's not what happens. This makes the sun go around the Earth even faster. And why would that happen? I guess the answer is commented right there. But the reason is that any transformation to the model matrix is applied relative to the parent's coordinate space. If it doesn't have a parent, then it's just relative to the global coordinate space. So I'm doing this rotation relative to the sun. Well, the sun's coordinate space, which is centered right here at the sun. And so that's why it's rotating just faster. Well, how do I rotate the moon around the Earth? And the way that I have to do this is like this. Keep in mind, there's matrix multiplication, so the order is this one, the bottom, then this one, then this one. We're left multiplying these. So I'm going to rotate or translate the Earth back to the sun, and 5 is just the units of that translation. Then I'm gonna rotate it around the origin. Then I'm gonna translate it back. And the effect is that it'll rotate around the Earth rather than around the sun. Let me see this. Okay. So that's pretty cool. Yeah. Actually, something... No, yeah, that's fine. So then we see this, which is pretty cool. You probably noticed that this has lighting. I haven't gone over lighting yet. So, you know, actually, this has a lot of new stuff that I haven't seen. How did I come up with these spheres? How did I do the lighting? So both of those. Well, you can start with the... Usually start with the spheres. These spheres are... I didn't write them on my own. These are stolen, basically, from 3JS. And there's a server running here that's serving up geometry data from 3JS and letting me bring that into Manim. Because 3JS uses WebGL, which is a variant of OpenGL, essentially. And so I could share the geometries between those. The broader idea behind this is that nobody creates shapes in OpenGL by, like, figuring out where to place these vertices. Where did I do it? You know, like what I was doing for the triangle, where I would like put this vertex here, put that vertex there, put that vertex there. If I wanted to do like a car or something, nobody has ever done that before by like placing vertices like that. There are programs that are specifically designed to allow you to model complicated shapes, get their vertices, put them into OpenGL or Blender, whatever, and render them that way. You should pretty much never reach the point where you're manually placing vertices around. Steal them from something else, or get them from a program, do something like that. But you shouldn't have to place those on your own. So that's where I'm getting the spheres. They're taken from 3JS. I could actually take a number of different things from 3JS. If I wanted this to be an icosahedron, then I can do that too. You can't really tell since the lighting, you can't see like curves or whatever, but this is an icosahedron. Or if I did cone, it'd probably be more apparent. Yeah, that doesn't super make sense, but this is a cone. All right. Why not the surface shader from Manim? That's a great question. The surface shaders and Manim, actually all of the shaders that we inherited from Grant are very strange. They don't have a concept of view matrices. They don't have a concept of model matrices. They don't have a concept of projection matrices. All of that was just written by hand. They're not factorable. They're difficult to use. They're just not that great. So that's why. Yeah, it should be possible to rewrite them in a way that does have a concept of these projection matrices, but I've just never done it. But that's why we don't use them just by default. The next thing we see is this lighting. Actually, I'll get to the lighting in a bit. Yeah, I think that's everything I wanted to cover about this. Wait, is it? Oh yeah, I guess I do have to do the lighting. Okay, here's how lighting works. I'm taking these shaders from 3JS. So standard material. A material is essentially a collection of shaders that determines essentially the fragment shader. Comes with the fragment shader. And the geometry is essentially controlling what happens in the vertex shader. So in this case, I took a sphere, that geometry, and I use it with this material called standard material. Now, standard material has a concept of lighting, meaning that if you pass in the normals necessary to determine the lighting, it'll compute that for you. The reason you have to pass in these normals is because, as you know from seeing fragment shaders before, they have to determine the color for each fragment essentially manually. You have to figure out how to do that with math. And you'll need a few things to do that naturally. You'll need the position of the lights, which are being passed to this shader up here. But you'll need the position of the lights, color of the lights, how strong are the lights. You'll also have to know, a normal representing where that surface is pointing, because light's going to be reflected naturally. And so it's going to be different if that shape is facing toward the light or, facing flat toward the light. Is it a virtual machine or full Linux? I'm running regular Linux. And so to make that computation possible, you have to have, normals with that geometry. Three.js supplies that for me, but I do have to update this normal matrix whenever I rotate. Okay. And so with that, that's more or less everything I wanted to, well, not really. That's a great deal of what I wanted to show, at least regarding 3D positioning and coloring things. So I'm going to go through this gallery. This is just sort of a showcase of different shapes and how lighting affects them. So this is a box geometry. This is a light. And I can move around this light. And when I do so, it'll show the way, I can move the shape too. But I wasn't trying to do that. It'll show the way that the light is reflected off the shape. Now a good example for this is what's called a torus knot, because it has a lot of shadows and stuff. And so I can move the shape around in the scene, as you can see the way that it'll interact with this light. And I think I didn't set this up to update the normal matrices by default. Oh, I did. Okay, so when I rotate this, you can see the side that's facing toward the light gets illuminated. The side facing away from the light is not illuminated. I'm going to go ahead and change this so that it doesn't update the normal matrix. If I can find that. Here. Okay, so here, this is what I'm doing essentially each frame. Pretty much the same thing, translation, rotation, and scale, computing that product. Then I'm updating the model matrix, which we know what that is, and the normal matrix, which is used for lighting. And I'm going to not update the normal matrix. Then I'm going to change this geometry. Then I'm going to rotate it. And you'll see if I rotate this, here the illuminated side is facing the light. If I rotate it like this, now the illuminated side is facing away from the light. And that doesn't make sense. And the reason for that is that the normals are being used to compute the lighting, and I'm not updating the normal matrix. So that's why that's happening. And to fix that, I have to update the normal matrix. And now when I rotate it, the illumination works properly. Okay. One other thing to take note of you can see here that this is what's called a standard material. This is essentially a shader controlling well, it's like a material. It's like the coding on the object. There are different materials. Standard is like more or less the most useful one, the most like quote unquote realistic. There's also a Phong material. And you can see when I switch this, it gets more shiny. It doesn't disperse the light as much. And it looks like that. And there's what's called a basic material, which looks like this. So the basic material doesn't respond to light. This is essentially what we had before when we just said frag color equals whatever. We just have something there and that's it. Nothing fancy. And then it doesn't respond to light. Now, if you really wanted to figure out lighting yourselves, there are some resources on that if you just like Google around, where you will actually use like the color of the light, the color of the material, the shininess of the material, the how rough the material is, things like that, and the normals. And you can figure out what computations are happening when the Phong material computes this light reflection, or the standard material computes this reflection. If you really want to do that. That's way beyond the scope of this, though. I just wanted to give you some intuition as to what's happening here. So that's lighting for you. Okay. So one last thing. We're going to take an aside from the straight 3D world we've been talking about before. I'm going to talk a little bit about using a full screen quad. If I can find an example with that. Okay. I got the example scenes. Oh, wait. There is a way to make games or graphics or virtual experiences, etc., by using only a single geometry. You'll have one plane. It'll cover the entire screen. You'll just do all the computation in the vertex shader, or in the fragment shader, sorry. And you can come up with very complicated, very intricate virtual experiences this way. You can also do that in Manim to some extent with this object, what's called a full screen quad. So mostly we've only been using pretty much two objects, shaders and meshes, and that's it. This, a full screen quad, is also a mesh, but it's a part of it that basically only requires a fragment shader, and it'll cover the entire screen. So this code, we can go through this really quickly. I'll just run it first. And I typed something wrong. And Manim's not letting me escape, so oh well. What's it called? Inline. Oh, I changed the, hold on. The one from example scenes. Cool. And I'll just close this window. That's a pretty neat graphic. And this is essentially, it's a single plane that's covering the entire screen, and it's running this code. So we can go through this a little bit. GL frag chord, what's that? This is a global variable passed to the fragment shader that represents the pixel that you're at in the viewport. So this is probably like 720 by or 640 by 360, something like that. So glfragchord.xy is going to range from 0, 0 here because it's outside of normalized device coordinates at this point. Let's go from 0, 0 here to 643, 60 up here. Then once we have that, we can do any computations we want to find the color for an individual pixel. So what this is doing is it's dividing that by the resolution. So essentially it's taking this value, which is in the range from 0 to 640 inclusive, and then 0 to 360. And it's dividing that by the resolution, 640, 360. So this is effectively moving it from these pixel units to 0 to 1. So that's what this is doing. But it's going to have the origin down here. So that's what this line is doing. Then it's essentially writing to this color variable. The way it's doing that is computing this vector to center. It's computing the angle of that vector. I can actually mostly just walk through all of this. This is your screen. This is GL frag chord. It's computing this angle to the center of the screen. So it's taking half, half, and it's subtracting ST. So this is to center. It's increasing that angle with time. So the angle that it's using is going to essentially rotate around like this with time. And it's computing that radius. It's also doubling the radius, which I don't know why it's doing that, but it's doubling the length of that vector. Then it's just going to use these three components as the hue, saturation, and brightness of a color. So it's the hue is going to be determined by that angle with this formula, angle divided by 2 pi plus half. The radius is that radius, and the brightness is always 1. So it converts that RGB and it just outputs that. So that's what you're seeing here. And when you understand that, you could use that to, for example, make this go faster. If I wanted this to be 2 times the angle just to make it go faster. Well, that didn't make it go faster. But you can see like what it's doing. It's now computing the color using twice the angle instead of once the angle. If I wanted this to go faster, I should do this, I guess. There, I kind of know what I'm talking about. Yeah, okay. Now this is doing a computation with, oh, whoops. That is not the button. With 3 times, oh, wow, that's trippy. Cool. But yeah, this is sort of showing how you can create these 3D experiences using just a single surface. One cool example, my background is actually a shader. And it's this shader. That's my background. And I can, now this is resolution dependent for the reason that I talked about before. So if I make this bigger, it gets bigger like that, which isn't necessarily what you want. So if I wanted that to look bigger when I make it larger, I can double that. This actually makes sense with that prior question I got about, does OpenGL have to know your screen size? And the answer is sort of, like, if you don't give it information about your screen size, it'll do like the right thing, but it just won't be necessarily the right shape. Okay, that's my background. And you may be wondering, where did you get this shader? Did you write it? No, I did not write it. I got it from ShaderToy. And you can go to shadertoy.com and it'll let you like play around with shaders that are written this way. This is not using most of the concept that we learned in this. This just has a single surface. It's all passed to a fragment shader that's right here. And you can just play with it that way. So for example, if I double the time here, that should make it go twice as fast. Or not. Oh, this is typed, I guess. So that'll make it go a little faster. And you can do like arbitrarily complex things this way. You can just go to shadertoy.com. And you can just see like all the creative things people have done using just a surface like this. And some of them, people have created like entire like worlds. I really appreciate you taking the time to walk through all of this. Can't wait to watch what I missed later. No problem. Hope you enjoy it. But there's like tons of super cool stuff that people do with just the fragment shader. All right, cool. I'm gonna stop that so it doesn't burn up my GPU. If you want to learn some more about how to do this, you could look into the Book of Shaders. That's another good resource for doing things with just the fragment shader. And it'll go over like, you know, how colors are computed, how you can mix colors, how you can shape things using functions, etc. Yeah, it'll let you like interactively play with these. One other good resource that I should mention before I finish up here is, I don't know the name of it, jcentel.com. But I'll just put these in the chat. These are good resources for learning about model view and projection matrices, and they helped me a lot in learning them myself. So link that one, that goes over model view and projection matrices. And this one goes over specifically projection matrices. Well, one thing that I actually probably should have mentioned at some point is that there are two types of projection matrices. I can just use this site to go over this, actually. There are orthographic projection matrices, which project a square, essentially. And this is what you'll see. And these do not encode any sort of perspective. And so, for instance, parallel lines will be parallel. Lines that are parallel, that are extending away from you. If you want a scene that has perspective, like the way that you see, for example, which if there are lines extending away from you that are parallel, they won't look parallel. It'll look like they converge on the horizon. And to have that sort of effect, you'll want to use what's called a perspective projection matrix, which looks like this, or it encodes a frustum like this. Okay, and this gives you really good intuition for like the near plane, the far plane, and you know, field of vision, things like that. Okay, so that's definitely worth looking at if you want to get into the nuts and bolts of this. And with that, I'll show you this cool thing I made. That's a nice animation. Now let me get rid of that. That's a nice animation. Pretty cool looking. And this doesn't do anything that you don't already know. This sphere is just a sphere. I took it from 3JS, basically. This cube is just a cube. You know how you could do that. This cone, you know how you could do that, but you know not to do it. You know to... Well, if you really wanted to write the code to do this, it'd be probably a good learning exercise. But I just took this one. And you know how to move the camera. That's just the view matrix. You know how to put lights in. You know to update the normal matrices to make the lights work properly. The only sort of mysterious thing is this M. So you may wonder how I did that. And if you ask yourself, well, did you did you place all those points manually? The answer is always no to that question. This is what's called an extrude geometry, which is a concept of 3JS as well. It's lets you take a shape, and this isn't that great an example for it, but it lets you take a shape, trace it out, and then convert that to a geometry which has some depth to it. Yeah. So I took this and I essentially passed that to 3JS. And like I said, all the code for that is on GitHub, so you can see how I did that. But that as well, I didn't do it on my own. I took that from 3JS. Cool, so that's everything I wanted to go over. And now you know how to render objects in Manim using OpenGL. Congratulations. So I can answer any questions if you have questions. Or other than that, yeah, I'll probably stick around a little while to just work on random stuff for a bit. Cool. No, I didn't mean to close that. I meant to keep it small. Like that. When to use triangles versus triangle strips. Well, you can use either. It's sort of a matter of what you're trying to do. I think triangle strips is useful if you're basically making something that's shaped like a strip. I think it's mostly used for lines. It's like if you want to make a ribbon, then triangle strips will let you pass in like this point, this point, this point. It'll do that. Then for each subsequent point, you can add one point, it'll just automatically do that. Then add another point, it'll automatically do that. At another point, it'll automatically do that. And the benefit of this is that if you're making a shape that's shaped like this, you get to save a bunch of vertices automatically. So you don't have to figure out the index buffer to do this. So that's when you'd want to, essentially. And there's also triangle fan. If you, I don't know, yeah, gotcha. Triangle fan, you can put in vertices like this. It'll do that, pass another one, it'll do that, pass another one, it'll do that, etc. So that's what that's for. The way we calculate the triangulation for surfaces right now isn't the way to go for the future. What do you mean by that? The way we calculate the triangulation for surfaces right now isn't the way to go for the future. Are you referring to the surface shaders that are currently in the library? That we probably won't want to keep using those? Mm-hmm. Yeah, so that's mostly true. The problem isn't really with the triangulation, though. The problem is more with the shaders themselves. Maybe I can just bring up those shaders. But those are some confusing shaders. It's like open Manim render shaders. And I could go to like quadratic Bezier. Actually, I think the surface ones might not be so bad. No, yeah, they're bad. Okay, so this is a shader that Grant wrote. And now we get to make fun of his is shader code. Okay. Oh wait, why does this is not focusing for some reason? It's cursed. Something to do with that, I guess. Okay. So this is taking in a vec3 point. Fine. It's calling this function position point into frame. What could that do? I think I can find this. Inserts position point. Okay, position point into frame. It has this option if it's fixed in frame. But it's going to take the point, subtract the camera center, and then rotate that point based on the camera's rotation. This is essentially a view matrix. This position point in the, oh man. Position point in the frame is transforming that frame as it should be relative to the camera's center and rotation. But it's done by hand. Then, let's see what this is doing. Get rotated surface unit normal. I think this is just computing the normal. This is probably like, I think this is fine. This is just being done because his surfaces account for lighting. The color is just passed as a varying. Then this position is moved by this get GL position. Thanks for the tutorial, it's really helpful. No problem. Then you can say, okay, what does get GL position do? Get GL position is a pretty monstrous function too. But let's go ahead and go through this example, which is if it's not fixed in the frame. And what it's doing is it's taking the x coordinate, it's scaling it. So we've seen this computation before. Divide by the world space x coordinate and multiply by 2. So we've seen this before. This is essentially applying a projection matrix that has this perspective scale factor. So the further it gets away, it's going to make things smaller. So this is computing perspective. It's doing it like this. And then I don't know what this is doing. If the perspective scale factor is greater than 0, this is to keep vertices too far out of frame from getting cut. I think this is his way of getting around the near plane and the far plane. From this comment, at least. It looks like he doesn't want things to get cut if they move too far out of the frame. And so he's doing this. But this is essentially a view matrix and a projection matrix, but they're not matrices, and they're very difficult to like follow things through. And so that's why we don't use these. It might be possible. It could be possible to like move this into a matrix and like move that into a matrix, but it'd just be a lot of work to try to do properly. And it just wasn't designed for it, so who knows if that's doable. Yeah. So we don't really want to use these. I wasn't trying to do that either. So in Manim, should we be looking towards each object using model view matrices, etc. passed to the shaders and let the GPU do the work rather than performing those operations on the CPU? Yes. If you can get away with it, it's better to do everything on the GPU. It's faster. It's basically just faster. It's faster. It's really parallelized. It's cooler. We want to be doing everything on the GPU that we can, basically. which will require some pretty significant refactoring, since a lot of the code that's in Manim wasn't designed to be used with these OpenGL concepts, and so unfortunately it's going to take some work to get that working properly. We should encode lighting in Mobjects too. Can it be done gradually, like on single classes to begin? Yeah, it definitely can. In fact, I'm slowly doing that. Oh, I forgot to mention. Like I said before, matrices, vectorized objects have already been retrofitted with model matrices. You can use model matrices on regular objects already. Hey, Blake4096, what's going on? But I wanted to mention that I'm currently working on a site to more or less just port all of the OpenGL that's on Manim to WebGL. And I can't do that much right now. I haven't put a ton of work into it yet. But it renders using Manim code that's converted to WebAssembly. Renders that with WebGL. And it's using the exact same shaders that are used in Manim right now. So that's pretty neat. I think in order for Manim to reach more widespread adoption, it's going to have a simple interface like a website for people to get started and to share things. And something like a website makes that really easy, really simple to do. And without that, I think it's going to be really difficult to get Manim more widespread adoption. I also wrote like this, which is the same thing, just like pretty basic. Oh, this is to show that you can make these interactive as well. So those will provide a way to make interactive graphics with Manim. And one day, it'll be really smooth. Right now, it can't do a ton. But we'll get there. Slowly. But we'll get there. Yeah, I just wanted to mention that. And that way, thanks, no problem. And additionally, that way, I won't have to like steal geometries and steal materials and steal lighting from Three.js. I can just use them. I can just drop them into the scene. I haven't done it. I haven't like put in the machinery to do that, but that will be possible if this is online. So that'll be super cool. What are the next steps in your opinion? For me, it's going to be getting that website to where this is as easy, if not easier, than using Manim natively, quote unquote, locally. Because I think this is just a much easier, much more useful interface to write things. So I'm going to be working a lot on that. As for what Manim should probably be doing is improving the infrastructure it has for OpenGL rendering. Most of it I think is already pretty good, but there are some changes to the shaders that need to be made. And it's kind of complicated to get into those. Basically, Manim renders curves, quadratic Bezier curves, with arbitrary precision. Meaning that if you zoom in on a Vim object forever, it'll never become like jagged. That'll never happen. And in order to do that, it makes the shaders much more complicated. I wonder if I have an example for that. Yeah, so here's some text. And well, actually, now that we know about the near plane, we know if I zoom into this a lot, they'll just disappear. because they're getting in front of the near plane. Actually, if I use Grant shaders, he has this workaround so that they don't get clipped through the near plane. So before I was using shaders that I wrote, these are shaders that Grant wrote. Although it's slower to zoom in on them. And no matter how far you zoom in on this, it'll never become jagged. And the trade-off for doing this is much more complexity in the shader. That makes it, I think, maybe not worth it. So I'm going to work on rewriting these by just like flattening these curves. And if I do that, then when you zoom in, it will eventually get jagged. But most OpenGL scenes have a near plane anyway. So if you zoom in too much, it'll just get cut off anyway. So it's less of a big deal for that reason. Yeah, but anyway, some improvements to the shaders, I think, are the next thing to do. And then beyond that, making it more interactive. I wonder what's going on there. Because I think Manim has a lot of potential to have scenes where, for example, you could see a visualization of some algorithm or some math concept, something. You'd see that visualization. And it'd be so cool to just have a link to like a Wikipedia page or whatever directly from that visualization. And that would make it a lot more easy to follow the concept that it's illustrating. And I think the fact that Manim can do that, but it doesn't have that ability for no real reason, is a significant detriment. I'm just looking at these shader bugs now. And that's neat. This is impossible to debug, by the way. This error will probably be here till the end of time because nobody can trace through those shaders well enough to fix it. You'll probably never run into that, though. Okay. Well, now that I'm done, I guess I'll go ahead and raid someone. Yeah, that was a successful tutorial. Let's see. I don't normally stream at this time, so maybe there's some... No, basically none of the programmers I follow, unfortunately. Just got the last bit. No problem. If you want to learn some OpenGL, you know, the video will always be there. So you can check that out. Oh, hey, there's me. I don't know any of these people because I'm streaming at a different time. I should do someone smallish. Maybe not that person who puts 18 plus on his stream. This person's using Python and Django. We can rate him. Well, let me see how long he's been going. 2.5 hours. Kind of long. This person more or less just started. But I think Python is more relevant. Okay, we'll rate this person. Okay, so let's say hi. And I'll see you in the next stream or the Discord or something like that. And I hope you learned something useful. Thanks. And I'll cut this